Okay, so the next one is the fourth one. Here we have to prove proposition 7 to 9. We will, as usual, we will first of all recall the statement of the proposition, then we will prove it in the solution. So let's recall the proposition. It is in fact that one, that absolute convergence test. Absolute convergence test. Instead of again writing the formal statement, let's just see what it says. So what it says is this: we have a formal series of real numbers which is absolutely convergent. Absolutely convergent. Then that implies the same series is also conditionally convergent, which just simply means it is convergent. So absolute convergence of a series of real numbers and infinite series of real numbers implies it is also convergent. So that's the main thing of this proposition. And when that happens, we also have this triangle inequality, that the absolute value of the sum of the original series is less than or equal to the sum of this series whose terms are the absolute values of the terms of the original series. So that's what we have to prove. So let's see the solution. And in proving this, we are in fact going to follow this hint. We are going to mainly use proposition 7 to 5, and proposition 7 to 5 is the one that we proved in the previous analysis video. So it's that thing which says that a series like this is convergent if and only if for every positive real number epsilon there is an integer m greater than or equal to m, for which these finite series where n varies from p to q, they all have their absolute values less than or equal to epsilon for all integers p and q greater than or equal to n. So it's that thing, this proposition 7 to 5. So we are going to use this now, and we use this immediately in the beginning itself. So it's given that this series is absolutely convergent. By definition, that just means that this series on the right hand side is convergent, and its convergence will imply those epsilon in those things, those conditions, by proposition 7 to 5. So we start off like this: since summation an, this is absolutely convergent for every positive real number epsilon there exists an integer n greater than or equal to m, such that we have seen this thing, so let's just rub this off. Such that the absolute value of these finite series are all less than or equal to epsilon for all P and Q greater than or equal to N. Since in analysis we encounter this kind of conditions again and again, so we don't explicitly mention that P and Q are integers. It's understood from the context that they are integers greater than or equal to N. Whenever they are integers satisfying this condition, then such a finite series has its absolute value less than or equal to epsilon, and this is coming from proposition 7 to 5. So we mentioned that also by proposition 7 to, if you want you can mention this here in the actual statement also, not within brackets, but same thing. Okay, so now something additional is also given in the hint. Proposition 714e, and proposition 714e is just triangle inequality for finite series. If you recall, it was this. Say you have a finite series like this, an, where say n varies from P to Q. Or to distinguish this from this thing, let us just consider Bn, where P and Q are some integers, such that Bn is defined for all integers lying between P and Q, including P and Q, and Q is greater than or equal to P, to avoid triviality. Then thus this sum satisfies this inequality. And this property is named triangle inequality of finite series, which is just part E of proposition 714. So now we are going to use that here. Now by proposition 714e, we have we are going to write two inequalities, and we will see what is going on here carefully. So by applying this proposition part E, we directly have just this. That is the first inequality. And then this in turn is less than, let me continue from here. this thing is less than or equal to its own absolute value. And that of course is less than or equal to epsilon for all P and Q greater than or equal to n. How do we justify the second inequality, that this is less than or equal to this? It is simple because these finite series after all are real numbers, right? In fact, we have the same thing here and here. So we have just simply used this inequality, that every real number is less than or equal to its absolute value. And we have equality here if and only if x is a non-negative real number. When x is negative, we have strict inequality. Like for example, if you take 0, then you actually get that equal to this. Also, if you take 2, which is positive, you get this. But if you take say -2, then you get this strict inequality. So that's what we have used in the second inequality, or in other words, that is the second inequality. So what now we have got is that this absolute value is less than or equal to epsilon for all P and Q greater than or equal to n. Hence, so we are again going to use that proposition. What was it? 7 to 5. Because proposition 7 to 5 is an equivalent condition for an infinite series to be convergent. So like when we started off with a convergent infinite series, we used the proposition to get these conditions, but then again such conditions we have got for this series, so we can go back to convergence. That's what we are doing here. Hence by this again, this is convergent. Or you can also write this is conditionally convergent, which just simply means that this is convergence. Conditionally, we have already discussed about it. We additionally say conditionally just to emphasize the fact that the convergence is ordinary convergence as opposed to absolute convergence. Okay, but that's not all. We have to derive that triangle inequality also. So for that, we now see this. Now, okay, so for triangle inequality, we are going to use that lemma again, yes. So by lemma 714E, we have shall I write it at once, or okay, we can just simply directly write what we are going to write. Minus summation absolute value of an where n varies from m to k. We will say what k is less than or equal to summation ordinary an where n varies from m to k, and that in turn is less than or equal to summation again absolute value of an, but this time plus this for all k greater than or equal to m. What have we done here actually? You see, for any say you consider this, say you consider one integer I lying between k and m like this. For any such integer I or index I, we have these inequalities. Okay, which is something that we already know about real numbers. So you have all these inequalities for as I varies from m to k. So what we have written here is the sum of those inequalities, and the fact that these sums also satisfy such corresponding inequalities comes from lemma 714 part E. So that's just what we have written. And this is true for all k greater than or equal to m. Hence, so we have inequalities like this. Now note that the things you see here, these three things, they are actually sequences of k. That is sequences where k varies from m all the way up to infinity. And these terms, the kth terms of these three sequences satisfy such inequalities. So this is a place where we can use the comparison principle. Recall that we encountered such a thing in the chapter on sequences, and furthermore we already know that these sequences, which actually are sequences of partial sums of such some infinite series, they are all convergent, because the two series that are involved in this situation are, one of them is this series, or rather this series. This series, which is given to be absolutely convergent. That means this series and this series, they are both convergent, and just now we have proved that this is also conditionally convergent. That means this is just simply convergent. So all these sequences of k are convergent, so we can use the comparison principle and take limits. Even after taking limits, the inequalities will be preserved. So hence, by the comparison principle, however, I won't write the comparison principle, but I will just write the number. Hence, by lemma 6, 4, 13. And when you are referring to these results outside of this book, outside of this text, of course, lemma 6, 4, 13 does not have any meaning. So there you can write by the comparison principle. Minus summation absolute value of an, where n varies from m to infinity, is by definition limit k tends to infinity. Don't have much space here, but anyway I will manage. n varies from m to k, but I should not forget that absolute value. Okay, so this just means this limit by definition, and this thing is less than or equal to, by the comparison principle, the limit of this. Which is equal to the sum of our original series, and that thing again is less than or equal to, by the comparison principle, the limit of this. So now you look at these three things. This is less than or equal to this, which is less than or equal to this. And after all, they are all real numbers. So this implies that the absolute value of the middle thing is less than or equal to this. So that is our triangle inequality involving the sums of this infinite series. So this completes the solution and also is the proof of this proposition. Next. This one is also proving one such proposition. Prove proposition 7 to 14, and it is that series laws. This one is very easy because the hard work has already been done when we proved sequence laws, that is limit laws for sequences. And also we proved the corresponding laws for finite series. That's why here it's more like you just have to mention the things and the parts will just drop out as consequences. And that is why the hint is also just that. Use theorem 6119, which is limit laws, sequences, for sequences. So we proceed like how we usually do. We will recall the parts of this series laws and we will prove them. this time I am going to write the statements of the parts within the solution itself, which however is just for the sake of showing the things here. The actual solution did not have the statements. So this has parts. Part A is just this. I just simply mention the thing roughly. There is no need to write the actual statement, of course. We have two series here, two series of real numbers. One is summation n varies from m to infinity. This is a convergent series and its sum is the real number x. And there is another series, summation bn, which is also convergent and its sum is the real number y. Then this infinite series an plus bn, whose terms look like this, is also convergent and its sum is just the sum of these two sums, x plus y. And there is a part B also. Let us write that one also, because B can prove these two things together. Prove means we will just simply mention what has to be done, and it is so easy that nothing much has to be written also. Let us see. In this case, in part B, here here we have the sum of two series. In part B we have the multiplication of a series by a real number, that is scalar multiplication. So here again we have an infinite series which is convergent. It converges to the real number x, and we have some real number c. Then this series is also convergent, whose nth term is c times an, and its sum is just cx. So now we are going to prove these two things. So the actual solution starts from here. Parts A and B of our proposition seven to 14 it is. Yes. Follow from parts A and B of theorem 6.1.19. Parts A and C it is written here. Okay. A and C of theorem 6.1.19, and it is extremely easy. This may be B also. Okay, I may have made a mistake in taking things down here. You will realize, you go to theorem 6.1.19 and you will understand which part we have used here. So now let us come to the question of how exactly are these parts following from these two parts. limit loss for sequences. The thing is this, you see, we are given two convergent series with their sums. So that means what? That means that the sequences of partial sums of these two series converge to x and y respectively, and those sequences of partial sums have these terms, which are the actual partial sums. The first one is this k, and the other one is this. As k varies from m to infinity in both the cases, so those are the sequences. These statements simply mean that these limits, the first limit is x, and the limit of this as k approaches infinity is y. So by part A of theorem 6119, that is sequence loss, this sequence is convergent, whose general term is this, as n varies from m to k. This sequence is convergent, and its limit as k approaches infinity is just the sum of these two limits. But these are actually partial sums of this series. So that just simply means that this series is also convergent, and the sum of this series is x plus y. So that's how you get part A of our proposition from part A of theorem 6190. And now I think you can clearly understand how one can obtain this similarly also using part C of theorem 6119. You just have to consider the sequence of partial sums of this that converges to x. So the sequence of partial sums of this series, the second one, which is c, whose terms are c times the corresponding terms of the sequence of partial sums of this, that also converges, and its limit is cx. So that's why the second series sums to cx. That's just it. So these are the first two parts of our proposition. Now next we see part C. Part C is not that straightforward, but still it's not very difficult. I mean, it's not significantly more difficult than these two things. So part C is this. We again have one infinite series of real numbers, and this time in the beginning itself we are not saying whether it is convergent or divergent or anything like that. And so this is one thing, and another thing is that k is a non-negative integer, or in other words a natural number. Then these two series, one of them is of course the original one, and there is another one where the index starts from m plus k, are either both convergent or both divergent. And when they are both convergent, we have this relation. the sum of the original series equals the sum of this finite series where n varies from m to m plus k minus 1 and plus the sum of this second infinite series. Okay, so this is the third statement of our proposition. Now let's for this one let us just write a sort of proof. Let S n and Tn n varies from m plus k to infinity be the sequences of partial sums of these two series. That is, the first one is our original series and the second one is that second infinite series. Respectively. Okay. Now we have to use one property of finite series, lemma 714 part A, by to relate these two sequences or rather their terms by lemma 714 part A. We have Sn equal to, let me write the sum also so things will be clear and we will see exactly how we are applying this lemma. N is varying from m plus k. Oh wait, this won't come from n plus k, but rather it will go from m to n itself. Okay, is that what we are trying to do? No. What I was going to write is correct. This is equal to something is wrong here. What I have written here is not true. Now it is not true. That is because in writing these partial sums, we are considering the partial sums of this series where the index starts from n. So in each partial sum, which is a finite series, the index will start from m, not m plus k. Okay, so this is equal to summation n varies from m to n plus k, okay, yeah, n plus k minus 1 plus summation n is equal to, then I have to write here n plus k. Things are getting tangled up here. M to m plus k. Okay, so let us not here also it seems like I have made a mistake. Let me just replace this n with small m plus k to n. We will see if things go wrong, we will adjust things, and that equals summation n varies from m to m plus k minus 1 plus this is Tn. But the question is for what type of n? For all n greater than or equal to m plus k. N greater than or equal to m plus k. Okay, let us now see what we have written is true or not. So we are choosing n to be greater than or equal to m plus k. Okay, just like what we have done here. Here the things are starting from m plus k. So we have chosen capital N to be greater than or equal to m plus k. Now note that when capital N is greater than or equal to m plus k, capital N is automatically greater than or equal to m. Why? That is because the k we have chosen to be a natural number. So k is a non-negative integer. So that's why we have got this thing. Okay, now let us come to this relations. So for such a capital N, Sn is what? Sn, because it's the sequence of, it's the nth partial sum of this series, is just simply such a sum where the index varies from m to capital N and the terms are an. Okay, so this is okay, and this equals this plus this, and that thing is coming from lemma 714 part A. You can write a finite series as a sum of two such finite series. And note one thing, that things here make sense because we are moving n from m to m plus k minus 1, and then the next value we are taking here from m plus k to n, and this thing becomes equal to this term, of course stays like we are not changing this here. However, we are writing T capital N. Is that justified? That is justified because this second sequence of partial sums is the sequence of partial sums of this infinite series where things are starting from m plus k. So if you write the nth term of this sequence, that is Tn, then it will be the finite series where the terms are an, the index starts from m plus k and goes to capital N. So that's why we have this thing, Sn equals this plus this. Let us just write that separately. That is Tn for all n greater than or equal to m plus k. So now you look at these two things, Sn and Tn, and treat them as sequences of capital N. So from this you can clearly see one thing, that when you vary capital N, Sn and Tn are changing. Okay, they are likely changing. However, this thing stays fixed, because all these things M, K, these were pre-chosen and they do not depend on capital N. In particular, they do not change with N, they stay the same. So Sn is equal to a constant which does not depend on capital N plus Tn. So from our limit laws of sequences, for sequences, Sn is convergent if and only if Tn is convergent. If Tn is convergent, then you add a constant to that, and that is nothing but Sn, so Sn is also convergent. And similarly, if Sn is convergent, then Tn is convergent. Okay, so from that what can we conclude? We can conclude from that let me just write the things instead of just simply saying. Thus, the sequences Sn, where n varies from not m but m plus k to infinity, and Tn, you may be thinking I have made a mistake here, but let me finish first. Where also n varies from m plus k to infinity are both convergent or both divergent. Where we have used our limit laws by theorem 6.1.19. This is perhaps the only theorem whose number for some reason I always remember. In case of convergence, we can take limit on both sides. This is equal to summation an as n varies from m to m plus k minus 1 plus limit n tends to infinity Tn. Now keep in mind that we are actually not saying something about the entire sequence Sn, because we have not started things with m but rather with m plus k. Unless k is equal to 0, we are actually not considering all the Sn's. But still, it does not matter. This difference does not matter, because do you realize that this sequence is a subsequence of the original sequence of partial sums? There is simply a difference in first few terms, and actually there won't be any difference if k is 0, but that is only a special case. Now, because a sequence that is convergent it continues to be convergent even if you remove finitely many terms from it, and also the limit does not change. So that's why limit of Sn that you see here, where actually Sn means this sequence, which is a subsequence of this original sequence of partial sums. This limit is going to be the limit of this sequence also. That means this limit is actually the sum of the original series, and this limit of course is the sum of that second infinite series. So let's mention these things. And in fact, we proved this fact in one of the exercises which I luckily have here, by that the first few terms of a sequence does not affect its convergence or its limit. Exercise 613. This is the sum of the series that is our original series. And because we are writing everything, so let's just mention that also, that this is the sum of the other series. Also, limit of Tn as n approaches infinity is the sum of this second one. Thus, so we can just now write this equation in terms of this series. Summation of an as n varies from m to infinity equals summation of an as n varies from m to m plus k minus 1 plus summation of an where n varies from m plus k to infinity, and that's what we wanted to prove. So that is the proof of part C, and there is one more also. It is part D. The statement of part D is just this. Here again we have an infinite series of real numbers which converges to some real number x, and there is an integer k. This time k is not necessarily a non-negative integer, it may be negative also. Then the summation of this theory, that is x, we need not even mention x anyway. This is also equal to the summation of this other, apparently other, actually there is no difference, other series, where the terms are indexed like a n minus k, and the index n starts from m plus k. So it's like we have added k to m, and to compensate for that we have subtracted k there from n. And here I won't go into the details, I'll just simply write this. Using induction and properties of finite series, prove that the series this, I think I need ink. That this series and the other one, a n minus k, have the same sequence of partial sums. That is, if you look at the actual partial sums, you will realize that they are actually the same. There is no difference at all. And you can prove that fact because you are saying something or stating this thing, that the terms are equal for infinitely many things, so you can prove it by induction. Have the same sequence of partial sums. So because the first one or the given one is given to be convergent and it has the sum x, so the other one will also be convergent automatically and will have the exact same sum. So I just end things here. So this is the, you see, in this solution actually we have gone very non-rigorously. It's not in fact a solution. Instead, you can just view it as a hint to an actual solution. So you have to write the actual solution rigorously, using all the things and filling in all the details. So that of course I leave to you. Now we move on to the next one. And this I believe is the last one in this set of exercises. It is, yes. Prove. This one also asks us to prove a result. Prove lemma 7 to 15. It's that last result, that telescoping series. And there is a hint. In fact, everything is there in the hints itself. So once you have the hints, you have the solution. First, work out what the partial sums work out the partial sums. Oh, exactly, the way it is written here is first work out what the partial sums would be. But I can change the way I write the sentence. an minus an plus 1, where n varies from 0 to n. So you work out these partial sums and prove your assertion by induction. So whatever you guess these partial sums should be, you have to prove that guess by induction. And so instead of a solution, here also I will give a rough sketch, which actually will have everything. You just have to write the solution neatly and rigorously. So what do we have in this lemma? We have a series which looks like this. Where this an is a sequence of real numbers with the condition that it converges to 0. So to see that this series is convergent, and in fact to know what its sum can possibly be, you just look at the partial sums. For example, when you consider this partial sum, say the first one, the first term of your sum, what do you get? You just have to put n equal to, substitute 0 for n. So you get a0 minus a1. Let's look at the second one. So here there will be two terms, a0 minus a1 plus a1 minus a2. So there is a cancellation and you have a naught minus a2. Because of these cancellations, actually a telescoping series has a very easy sum to calculate. Not only is it convergent, but the sum is also very easy. Let's look at another one. By now you already have seen what this one will be. So this is going to be a naught minus a1 plus a1 minus a2 plus a2 minus a3. So these intermediate terms, they cancel out and we are left with a naught minus a3. So the thing that we are guessing about these partial sums is that for any natural number n, this is equal to a naught minus an plus 1, where n is any natural number, because that's what we see there, it's happening. But these of course are only 3 cases, whereas what we are stating here is for infinitely many n. So that's why you need to prove this by induction, which is absolutely straightforward. Okay, so now to find the sum, you just have to find the sum or see that this series is convergent. You note this thing. Yeah, now only when things are about to end, the ink is coming properly. You have to look at this limit as n approaches infinity. So this is going to be, by the limit laws, a naught is independent of n, that is, it does not change. So the limit will be a naught minus limit of an plus 1. But it's given that the original sequence an is convergent and it converges to 0, so this limit is 0, and that's why this is equal to a naught. So the sum of our telescoping series is a naught, and that's what lemma what was it, lemma 7 to 15 states. And things end here. So this completes this set of exercises also. Next we can move on to series with non-negative terms, that is series whose terms are non-negative real numbers. Now before I wrap things up, let me just say one thing. You see, whenever we see some piece of mathematics, usually what we see some symbols, and we learn what those symbols mean, and we understand something. That is okay, that is fine, but there is a very bad way of going through things or learning things, that is the mechanical way of actually going through all the things, verifying that each step is true, ending with the last stage and then stopping. and not looking at the entire thing with a global perspective. If you do that, things will go very easily. Okay, of course you will encounter difficulty, you won't understand something, but then with perseverance you ultimately understand that step. So you look at the individual steps, you understand the steps, and that's it. Things end and you go home, and then you forget everything. So why this thing happens is that you fail to, after ending the things, after ending the formal verification of the things, you fail to look at the entire thing globally. That is, what actually went on behind these symbols. That's what mathematics is. Mathematics is not these symbols, of course, but rather what they mean, or what lies behind these symbols. That is because you can change the symbols. You can, for example, write all these things not in English but in some other language, or you can, for example, instead of using LIM to denote limit, you can use something else, some other symbol. It does not matter. So what goes on behind these symbols is what really matters. And that's why you see, why do we consider isomorphic groups to be actually the same thing? It's because the idea, the group structure that is behind those two representations is the main thing. So when you look at that group from one point of view, it looks like this. When you look at that same group from another point of view, it looks totally different, but what lies behind these two representations is the real main thing. So you try to have that global perspective. Of course, when you write mathematics down and when you present things, you have to be rigorous so that things look the way they are supposed to look. But behind all these symbols, the real thing should be intuitive in your mind, which naturally would be vague, but that should be there, without which mathematics is just simply a sea of meaningless symbols. Maybe meaningful symbols, but boring, dull and uninteresting symbols. But really, what is going on behind these particular steps, for example, what goes on inside a telescopic series? You may have noticed that I have not written down a formal solution. I have done that deliberately to show you that, okay, the partial sums behave like this, and that's why we guess at something like this. Instead of going through these things, if I just simply write this, which may look like, okay, it should be true, and then you use induction to prove this, that also can be done very easily, but you won't know how one comes up with this in the first place. So that thing should be there. That, of course, I cannot all the time show you here when I am going through things, that you have to do for yourself. So that's it for tonight. And the next what we should do, we have already gone through groups, fields, vector spaces, calculus also we have done once more. So let's do number theory this coming Tuesday. So that will be all. So until the next time, this is me, Lucifer, from a mathematical room. Have a nice night.